This video shows how to make a map to show the validation of a land change simulation model. We introduce the concepts of wrong hits and of unpredicted transitions, which complement established measures of misses, hits, and false alarms. Our concepts help to reveal why a simulation model makes errors. A land change simulation model uses maps from a calibration interval to set the model's parameters for the subsequent simulated extrapolation. These two maps show the start time as 1971 and the end time as 1985 during the calibration time interval for a study site in suburban Massachusetts in the United States. The maps have three categories. Category 1 is forest, 2 is other, and 3 is built.
This map shows the reference change with persistence in gray during the calibration time interval. The map shows colors for three transitions: forest to other, forest to built, and other to built. The table at the right shows the 1971 category in the rows and the 1985 category in the columns. There are 0 pixels for three transitions: other to forest, and built to other. Because those transitions do not exist during the calibration time interval, a land change simulation model extrapolates the transitions that occurred during the calibration interval. These two maps are the reference map at 1985 and the simulated map at 1999, according to a run of Teraset's land change modeler. The difference between the maps is the change that Teraset's land change modeler simulated based on an extrapolation from the calibration time interval.
This map shows the simulated change during 1985 to 1999. The simulated change has the same three transitions that existed during the calibration time interval, which are forest to other, forest to built, and other to built. The Markov matrix shows positive proportions for these three transitions and 0 for the three transitions that do not exist during the calibration time interval. We call those three transitions of 0 simulation and unpredicted. Simulation leaves those unpredicted because those three transitions have 0 size during the calibration time interval. These are the reference maps of the validation time interval from 1985 to 1999. The difference between these maps shows reference change during the validation time interval.
This is the map of reference change during 1985 to 1999, showing 3 shades of gray for persistence and 5 colors for transitions. Those transitions include other to forest and built to other, which are transitions that do not exist in the simulated change because those two transitions do not exist during the calibration time interval. Thus, the simulation model will not simulate those reference transitions correctly because the Markov matrix has zeros for these transitions, which we call unpredicted transitions. This is our validation map, which we created by using the crosstab module in Teraset, where the first image is the reference map in 1985, the second image is the simulated map of 1999, and the third image is the reference map of 1999, with a mask to indicate the spatial extent. Each number in the legend denotes the categories where 1 is forest, 2 is other, and 3 is built. We classify each combination as one of 7 types. Correct rejection is a pixel that is the same category in all 3 maps for a category that experiences simulated loss according to the Markov matrix. False alarm is a pixel of simulated change where there is reference persistence during the validation interval. Miss and unpredicted is a pixel of reference change during the validation interval, but simulated persistence because the Markov matrix has 0 for the particular transition. Wrong hit and unpredicted is a pixel of reference change during the validation interval and simulated change to the wrong gaining category for a transition that the Markov matrix does not have a simulation of that transition. Wrong hit is a pixel of reference change during the validation interval and simulated change to the wrong gaining category for a transition that the Markov matrix shows positive transition. Hit is a pixel of reference change during the validation interval and simulated change of the correct transition. Built persistence is distinct from correct rejection because built never loses according to the Markov matrix. So built at 1985 is not a candidate for loss. Thus, the label of correct rejection would not be appropriate.
The image on the left is a validation map that Terraset's land change modeler produces, which shows false alarms, misses, hits, and 0 elsewhere. Our validation map includes 4 novel improvements. Our map uses the white as the background to delineate the spatial extent. Our map distinguishes hits from wrong hits, which the land change modeler calls a false alarm, as in the combination 2, 3, 1 in the legend. Our map designates the transitions that are unpredicted according to the Markov matrix. Our map distinguishes between correct rejections versus categories that experience 0 simulated loss according to the Markov matrix, such as built. An effective validation exercise gives insights to the reasons for the simulation's errors. The new concept of unpredicted transitions is important because the Markov matrix is responsible for those errors, while modification of the simulation's allocation cannot fix those errors. It is helpful to distinguish correct rejections from persistence of categories that do not have simulated loss, because those categories at the start of the simulation are not candidates for simulated change. We recommend you read this article concerning land change model validation. This publication explains other concepts for how to validate a land change model. Kyle Peksock, Maria Biles, Professor Pontius, Clark University, and the Long-Term Ecological Research Network facilitated this video. For additional videos and publications, please visit Professor Pontius' website at the link provided. Thank you.